Hi, this is lecture 4 for the summer session of MEC 3820 heat transfer. Just to give a quick outline, we're going to start with the conduction rate equation and develop the heat diffusion equation, which is a differential equation that will describe the conduction through a solid, and we'll then talk about the types of boundary and initial conditions that are required for this differential equation. So in layman terms, we're going to develop a physical model. We're going to convert that model into a mathematical form, i.e. a differential equation, and then we'll obtain these particular solutions that are of interest to us. So we'll start with Fourier's Law, which we know as being the conduction rate equation, and we've stated that this is empirically derived. So Fourier's Law gives us the amount and direction of the rate of heat transfer through a solid. In this case, the rate of heat transfer is q dot x. And notice it is a vector, and I have it being a vector in the x direction using the I unit vector. And if we then substitute in the form of Fourier's Law, it's minus Ka delta T over delta X, where K is the thermal conductivity of the material. All right, so we know from the second law that heat is going to run downhill, right? So that is going to define the direction of the rate of heat transfer, so from a high temperature to a low temperature. But what we're also doing is we're defining a coordinate system. So the coordinate system is up to us, or the person solving the problem, as to which side and which direction they would want x to move, or their x coordinate to be pointing. So in this case, I have the left-hand wall marked as T1 is going to be at x1 equals 0, and the right-hand wall, which is at temperature T2, at position x2 equals L. And what we're essentially doing, right, delta T over delta X is the slope of a line. So we're going to go the rise over the run. So from T1 to T2, the rise is T2 minus T1. The run is x2 minus x1. All right, so that defines our Fourier's Law for this situation. Now let's evaluate it for different cases. So for the case where T1 is the high temperature and T2 is the low temperature, that's essentially what's shown here in the figure. And we're expecting the heat rate to move from left to right in the positive x direction. Well, if that's the case, T1 is the higher value and T2 is the lower value, so the numerator here is going to be negative. But this negative value times the negative value that's included in Fourier's Law makes this entire quantity positive, showing me that the heat rate is going to go in the positive x direction. Now, if we evaluate for the other situation where T1 is the low temperature and T2 is the high temperature, in that case we would expect Qx to be pointing in the negative x direction. So let's verify that that works. So if T2 is the high value minus T1, the lower value, this numerator is going to be positive. So positive times the negative will give me an entire negative quantity, which will then define the direction of the rate of heat transfer in the negative x direction. All right, so that's what the deal is with the negative sign. It's therefore making sure the direction of the heat vector, or the direction of heat is correct. All right, so let's look at a very quick example. So we have a wall made of plate glass. It's 2 millimeters thick. Plate glass, if you look in the back of the book, has a thermal conductivity of 1.4 watts per meter per Kelvin. The left-hand wall, which we'll say is x equaling 0, is the inner wall in this case, so T inner, and the surface temperature is 18 degrees Celsius. The outer wall, or T2, right, is going to be the surface temperature of the outer wall is 33 degrees. So if we want to calculate the rate of heat transfer through this solid, we'll use Fourier's Law, so Q dot X equals minus Ka delta T over delta X. But we're not given an area in the problem, so we're going to utilize the heat flux. We'll take the heat rate and divide it by area, and the units will become watts per square meter. And this is the general case. If you're not given the area of a problem, for a particular problem, you divide it by a unit area, in this case 1 square meter. And your answer is going to be coming out, and how many watts of heat is transferred per unit, per square meter of the wall or the substance that you're working with. We're assuming we're assuming an infinite flat wall for most of our cases here. So negative thermal conductivity, T2 minus T1, or in this case, T outer minus T inner, and 2 millimeters, right? That's X2 minus 0. So we get negative 1.4 watts per meter Kelvin. This ends up being a positive value of 15 degrees, right? So now I'm making this kind of my own notation here, just reminding you that when you're doing a delta T, whether the units are degrees Celsius or degrees Kelvin, it doesn't matter. It's going to be the same quantity of 15 degrees. And in that case, this term here cancels with the Kelvin term that's explicitly called out when you're looking up, say, the specific heat of plate glass. Go ahead and then, of course, we got to convert our millimeters into meters to make our units work out, and we end up with a value of negative 10,500 watts per square meter, or if we want to, we could write it in terms of kilowatts. We note that the heat flux has a negative quantity, which means that the heat is flowing from the outer surface towards the inner surface, which of course makes sense since the outer surface is 33 degrees and the inner surface is 18 degrees. All right, so we have the Fourier's law, and if we, right now it's delta t over delta x, but if we allow delta x to approach 0, we get the differential equation, right? We get the derivative. So dt dx, the first order differential equation. And now we're looking at this in just one-dimensional Cartesian form if I'm only looking at the x coordinate. But in general, right, we can apply Fourier's law to a solid in 3 dimensions. And if I was going to write that in Cartesian form, that would be x, y, and z. So what we would end up in this case, we would end up using the gradient, right? So Calculus 3 rears its ugly head, right? You learn this stuff for a purpose. So Fourier's law written in flux form is minus k gradient t. And notice in this case, we're using partial derivatives, right? Because now t is explicitly a function of x and y and z. So that's very important for us to realize right now. So in the general 3-dimensional form, we have a temperature field that we would have to specify an x, y, and z coordinate and then use our solution to find out what the temperature is. And of course, if we're sticking with a one-dimensional format or a one-dimensional case, we just have temperature as solely a function of x. And that's primarily what we're going to be looking at for the majority of the problems in this class, or this first bit when we're dealing with one-dimensional conduction. So now we are saying that this derivative is going to be a derivative of a function t as a function of x. Now, I know I've stolen the thunder already by indicating that it is going to be this straight line, but we don't know at this point, right? We have this empirically derived equation, Fourier's law, and now where we originally called it delta t over delta x, but now when we say that we have to create a function, we still might know that it's T1 and T2 on the left-hand and right-hand walls, but we're not sure what the shape of the function is. All right, so that's something that we're going to be proving right now. And we're also going to have leave open the possibility of transient heat conduction. So we could end up with a case where the wall is hot to begin with, and this would be, say this is the realistic temperature profile that's existing at time t equals 0. And then as time marches on, this profile would change with time. So this would be the transient or the unsteady case.